This is part 2 of the tutorial for lesson 8.3, Number of Solutions for Linear Systems. In this tutorial, we've been looking at how to predict the number of solutions for a linear system by comparing the slopes and y-intercepts of the equations from the lines in the system. When comparing the slopes and y-intercepts, you have to look at the equations and see if they're the same or different. If two lines have different slopes and the same or different y-intercepts, it doesn't really matter about the y-intercepts, then there's one solution because those two lines will meet at one point. If the two lines have the same slopes but different y-intercepts, they will be parallel and will never meet, so therefore will have no solutions. And two lines that have the same slopes and the same y-intercepts are in fact the same line, and will have an infinite number of solutions. So let's look at the last examples of how to use this information. In this example, we have 4 vehicles traveling along a straight stretch of the Trans-Canada Highway. Their current distances and speeds are shown in the table. We have 4 different situations. We have a car, a minivan, a truck, and an RV. And it gives us the current distance, probably from the starting point of each vehicle, and the current speed in kilometers per hour. For each vehicle, we want to represent it as an equation, a distance-time relationship using a system of linear equations for each pair of vehicles. Suppose that the vehicles continue at their current speeds. Identify and interpret the solution to each linear system. So first we need to identify a couple of variables that we can use in each equation. So our first variable is going to be d, and we're going to use it to represent the distance traveled in kilometers, and then we're going to use t to represent the time traveled in hours. In part A of this question, they want us to compare the car and the minivan. So we're going to set up equations to represent each one. For the car, the distance that the car has traveled is going to be equal to 90 times the time, because it is traveling at 90 kilometers per hour, and if we times that by time, that will tell us how far they've traveled in that amount of time, plus the initial distance, which was 40 kilometers. Add those together and you get the car's total distance. Similarly, for the minivan, the distance that the minivan has traveled is 90 times t, because it's also traveling at 90 kilometers per hour. Times it by the time to get that distance, plus the 25 kilometers that it already had gone. Now, if we compare these two equations, we notice that the slopes, or the speeds, are the same. When their speeds are the same, they're traveling at the same rate. But their starting points were at different distances. So these two cars are traveling along at the same speed, but at different distances from the start. So they will actually never meet. They will never be, one will never catch up to the other. Now, as a system of linear equations, there would be no solution to this system. Again, because those two lines would never cross or meet. So there's no solutions. Let's look at example B now. Now B, we're comparing the car, but this time to the RV. Alright, so the car, we already had the equation. The distance that the car has traveled is 90 times t plus 40. But the RV's distance traveled is going to equal to 90 kilometers per hour times time, plus its initial distance of 40. Well, because these two vehicles are traveling at the same speed, but they also started at the same point, they will actually be driving, well, basically side by side the whole time, and would be always at the same point. Therefore, this system of equations would have an infinite number of solutions. Infinite solutions, because again they meet at every point. And in part C, we are going to compare the truck and the RV. So the truck's distance can be represented by 110 times t, because it's traveling at 110 kilometers per hour, plus the 30 kilometers that was its starting distance. And we already had an equation for the RV. It was traveling at 90 kilometers per hour times time, plus the 40 kilometer distance that it started at. Now we notice that our y-intercepts, or our starting points, are different, and so are the speeds or slope. Because the slopes are different, right, the truck is traveling faster than the RV, and therefore it will eventually catch up. So these two lines, if you were to plot them, there might be the RV and there might be the truck. So the truck had a smaller starting point than the RV, but the truck is going faster, so it has a faster rate of change and will eventually meet and pass the RV. So there would be one solution to this system of linear equations, and that's time. So in conclusion, for lesson 8.3, we have some key ideas. For the first one, a system of linear equations can have one solution, no solution, or an infinite number of solutions, depending on what the two lines look like compared to each other. Before solving, you can predict the number of solutions by comparing the slopes and y-intercepts of the line's equations. If they're intersecting lines that have one solution, the equations will have different slopes and the same or different y-intercepts. It's the slopes that are different that will clue you into this one, and that's one solution. If they're parallel lines, and they will have no solution, and parallel lines have the same slopes, but they have to have different y-intercepts as well. And lastly, coincident lines have an infinite number of solutions because they are the same line, and their equations will have the same slopes and the same y-intercepts. So it's infinite number of solutions. For some linear systems, reducing the equations to lowest terms and comparing the coefficients of the x terms and y terms and constants may help you predict the number of solutions without actually have to rearrange the equations into y equals form.